So welcome again to our research methods lecture. This time we will focus on what could be called logical reasoning or formal approaches, or in mathematics people call it proof techniques. There are many names for it and they stretch from somewhat informal to fully formal. Let me explain. Logical reasoning is a fundamental aspect in any kind of research. However, if people talk about being logical or making sound logical reasoning, they are often not really very precise. However, in mathematics, very precise techniques have been established to provide a sound basis for formal and logical reasoning. We will not go into every depth of logical reasoning because you could make a complete lecture only on this topic. However, what I want to do in this chapter is to introduce to you the relationship of formal logic to the overall field of research methods, what's their place and what's the contribution there is for this kind of approaches, and also what cannot be done in such a way, so you can decide, depending on the context, whether to apply a formal approach. And I also want to provide you with some standard equipment, so to say, some standard proof techniques. Some of them you may already know from mathematics, others not. That might also depend on where you did your bachelor degree. The main focus of mathematical proof techniques is to ensure that we derive correct conclusions. Within the overall framework of our research description, that means where we differentiate the theory level from the empirical or observational level, mathematical proofs or logical proofs are fully in the theory level only. And that's actually something that distinguishes them from other kind of approaches to other types of research methods. So formal approaches can be used as a basis for drawing conclusions within a theory or within a model of reality. It's actually not really going beyond that. However, then, if we have this conclusion, we can in turn use this model and apply it to make predictions about reality. And that's actually how we typically evaluate our theory. However, whenever we look into formal reasoning, there's something which is often neglected, but I think it's very important to realize. If you draw a conclusion from a theory, it is guaranteed to be absolutely correct if you applied sound logical reasoning. However, it is preconditioned upon the adequacy of your assumptions. That means no matter how fully logical sound your derivation is, if your assumptions are wrong and they are not corresponding to reality, then your outcome will be wrong. So, how is formal reasoning embedded in the rest of research methods? Experimentation and experimental methods we will discuss in more detail later on. Experimentation allows us to construct theories based on observations. That's actually the main goal that we have with them. Then, on the other hand, formal approaches enable us to reason within such a theory. This leads to new predictions. So, if we have an assumption A and that holds, and we establish it, for example, in an experimental way, then B must also hold. This is a kind of reasoning that we get. Note that in this way, B is preconditioned upon the correctness of A. And then we can use that as a goal for further experimentation. We can say, all right, now we established if our theory is correct, then B must be observable. Now we can do an experiment to validate whether B is correct. That's also called falsification. And the idea is a good theory will show us, based on some predictions, that it can fail. If you have a theory where you cannot make derivations that can also be disproven, then you actually do not have a sound scientific theory. So going back to this picture that we had earlier, so we abstract such cause constructs and effect constructs based on experimentation. Many such cause-effect relationships will establish our theory, and then we can use this combination of cause-effect constructs within purely the theory level to make formal derivations of consequential cause-effect constructs or observational expectations. And then we can go back to the observation level, to the empirical level, and compare that again to reality. But the part we are talking about in this chapter is purely on this upper half of the picture. We will only talk about the aspect of how do you actually make derivations within the level of theory. So what are the benefits of such formal approaches? First of all, it's provability. It is, if you do it right, there's no way around it, it is correct. And that's a big wow. That's a big benefit as opposed to all other kinds of research methods. It also works for all quantified statements, meaning we can derive statements saying that whenever X, then. That means we have a very large number of potential observations that our conclusion applies to. This is very unlike what we typically get from empirical work. On the other hand, and that's kind of a negative point, we will need to evaluate in the end whether these assumptions are really correct. Because if our assumptions were wrong, then also our conclusions will be wrong. So that's actually one of the goals. For that reason, we can say these logical derivations, they aim at providing us with a better basis for further empirical work. That means we are not restricted in our empirical work to just make analysis based on what we already have in our theory, but based on derivations we made which point to secondary or other effects. Several weaknesses of formal approaches also exist. They can be pretty much effort, because formal approaches or proof techniques and such can be very complicated. If you apply them as a human, that can be a lot of effort, but also to some extent they can be automated because there are things like automated reasoning techniques, so-called theory improvers that support you in such derivations, and that is also very computationally expensive. And that's often a challenge. We need to provide a clear logical basis. That means we have to describe our theory precisely enough that it really is, that formal approaches can be used and applied to it. How difficult that is very much depends on the context. However, I would claim that whatever you do, there's value in even trying that, because this makes the underlying basis much more precise and therefore helps in clarification of the theory, even if ultimately you're not applying a formal method. So what is a theory? We already used the term theory in an informal way many times in our discussion. So we started with the distinction between the theory level and the observational or empirical level, but we never precisely defined what we mean with theory. So here's a definition. First, we define what a statement, a formal statement, is. That's basically a sentence that can be true or false. Like, all people are less than 3 meters high. Yeah? So that can be true or it can be false, and we can evaluate that relative to reality. Such a statement is called a proposition. A formal theory, then, is a set of such statements that may relate, or that will usually relate, to a common set of individual concepts, and further describes a field of knowledge that we are interested in. Given these definitions, what is a proof? A proof derives the correctness of a formal statement from a set of axioms. These are assumptions about the fields. They are not necessarily given, and previously proven statements. So these are, or the basis for these assumptions might be either they are ad hoc assumptions in the sense of we just make this assumption, or it can be based on some evidence that this makes sense to make certain assumption. A proof consists of a sequence of proof steps, each of which directly follows from the axioms, previously proven statements, and the preconditions of the statement, ending with the conclusions of the theory. What that finally means is we establish by pure logical reasoning that something that we did not know before has to be true if the axioms are true. That's a very strong statement. Just let that sink in. It's really, we show that it's absolutely sure that if what we assume in the axioms, what we already derived, then we know for sure that the results also are correct. The big question mark, of course, in this picture is, are the axioms, are the assumptions correct? Yeah. In our theory picture, and I go back to that for a moment. In our theory picture, these kind of assumptions or axioms, they are driven by observation typically. That means we see something, this leads us to conjecture a certain statement. This results in an assumption for our theory. We use that as an axiom in our formal reasoning, and as a result, we get a new conclusion, a new cause-effect construct, for example, and that is something we can then validate relative to reality again. So proof is simply logical reasoning taken to its extreme. Many people talk about being logical, when you have a proof for it, you know it's really logical. There are many different proof techniques, and there's a lot to be said about the details and the techniques of doing proofs. We cannot go into all of that because we do not have the time for that. However, here are some proof techniques you may perhaps know, at least superficially, from mathematics. I want to briefly discuss these 5 with you in this lecture. These are the direct method, the proof by cases, the contradiction, the induction, and the contrapositive method. Next, let's come to our exercise. The question is, does formal reasoning allow us to prove that something will happen in reality? I list below 3 different options. Have a look at them and establish for yourself what do you think is the right option. Stop the video only when you come up with your conclusion, then restart it. Welcome back. Now let's discuss the 3 possibilities here. So the first, yes, formal reasoning allows us to make correct statements about future observations. This is not quite right. So formal reasoning allows us to make statements about future observations. They are in theory correct in the sense that they follow from the assumptions that we made, but it's not necessarily correct statements about future observations because reality may show different behavior if our assumptions were wrong. B, no formal reasoning only allows us to draw conclusions about theory. Well, to some extent that is correct because what we get from formal reasoning are conclusions on the theory, for example, other statements that are supposed to be correct, but actually it goes a step further. We want to use it to draw conclusions about reality, and it actually makes probable statements about the reality. Or probability is not the right term, so it makes statements about the reality that are correct if our assumptions are correct. And that's actually what the third case tells us. Formal reasoning allows us to establish assumptions, what should be observed if our current theory is correct. That means it really tells us what should probably be the result of our observation, but if our assumptions are wrong, the reasoning may be wrong. Richard Feynman is said to have summed up pretty nicely in this short sentence. It doesn't matter how beautiful your theory is, it doesn't matter how smart you are, if it doesn't agree with experiment, it's wrong.